All right, welcome everybody. I'm sorry that I'm getting into this so late. This is I think now the fourth attempt to get this recorded and get it recorded right. A couple of times I've tried it, audio didn't work, and just lots of different stuff. So here we go. First thing to note: final exams next week. If for this class they are teacher made, finals, and so that means that you're going to be taking the test from 11:30 to 2:30. That is independent of when you are normally in my class, and so those that need to pay most attention to that are my first period students. First period, you'll take it on Monday the 14th. Third, you'll take it on Wednesday the 16th. I know that Wednesdays are usually our kind of off days, but the test is Wednesday. Fourth period, your test is going to be on Thursday, and again, all of these are at that 11:30 period. It is remote only, so if you are part of that the A group on Monday, or if you are part of the B group on Thursday, you don't go to school, not for my test. Okay, you're going to stay home. You're going to take the test remotely. If there is something going on where there is an issue, you need to let me know absolutely as soon as possible. Just absolutely as soon as possible. It is open notes, and attendance is mandatory. You can get a 0 on the final. Okay, that is allowed. I can't do it for the 6 weeks, but I can do it for the final. And if you do not test within the testing window, you can get a 0. And the only way that you get an opportunity at a retest is you need one of the acceptable absence policies that's in your student handbook. Things like, you need the doctor's note saying that you were unable to take the test. You need to have a note from like a lawyer saying that you were participating in some kind of a court activity or something like that. Just a note. Sorry, they slept through their alarm. You get a 0. Okay, I can't stress that enough. It needs to be, if you're going to miss it, there needs to be a highly justifiable reason. Okay. It's also, this is an open note test. There are some open resources, that you are going to be allowed to use. That will be available to you. And I'm even going to show you the one that I use, which is Desmos. You can use Desmos on this, and I'm going to demonstrate how to simplify some of these things. Some of the main things that I want to go over right now. This is just kind of for review. This is predominantly for my fourth period because I couldn't make it into fourth period today. But this is there for others of you as well. A couple of problems. Identify the resistor whenever you're given a resistor and you're trying to identify what kind of resistor it is. Remember that fourth resistor is the tolerance, that fourth stripe on the resistor is the tolerance. For our problems, you ignore it. Okay, just pretend that it's not there. And so what you're focusing in on are the first 3 primary lines. If you want to create an equation, to kind of help simplify what this is it would be 10 times that first stripe plus the value of the second stripe times 10 to the power of the third stripe, and so then you can actually just plug that into a calculator, and that would give you the number. But we're gonna see here that that can be a little bit more simplified. Now on the test there is I am giving you a code table, so that way you know what the colors represent. I can't pull that up here on my device right now, but I am looking at it, and it's whatever the color number represents. It doesn't matter which band in the first 3. It's so like red is a 2. Red is a 2. And it doesn't matter where it falls. It's going to be a 2. The green is a 5. The green is a 5, and the orange is a 3. Yellow is a 4, and blue is a 6. Okay. Now, if you follow these kind of as is, first I'm going to show you how to work using this equation here, and then we're gonna build up from there. So this is, sorry about that. Okay, this is 10 times 2 plus 5, and this is a group. So I'm going to put it in parentheses. And then this is times 10 to the power of 3. Okay. Now this would be the full formal way, but you're gonna see that there's a shortcut. There's going to be a shortcut to it. All right. 10 times 2. 10 times 2 is 20. All right. Plus 5. And times 10. And the thing about 10 raised to any power is that power, that exponent, simply tells you the number of zeros that go behind the 1. So 10 cubed, or 10 to the power of 3, is 1,000 because it's a 1 with 3 zeros behind it. So that's going to make it a little bit easier. And 20 plus 5 is 25. And then this is times 1,000, and so what you get, 25 times 1,000 is 25,000. Okay, and this is how you would write your answers. I think it's okay if you put the commas in there, but if you leave the commas out, it is okay. What is not okay is doing something like 25K. Okay, don't do that. That is not going to register well. And if I remember correctly, you shouldn't even be able to. But what I want to point out, the next little piece that I want to point out here is, look, it was 25 times 1,000, and then you get those first 2 digits, which were 25. And so that's a shortcut. That's a shortcut that you can read, because let's take a look at this next one. The black band is 0, by the way. The black band is 0. So what happens is this 4 times 10 is 40, plus 6 is just 46. And then this is times 10 to the 0. Anything to the power of 0 is 1, so 46 times 1 is just 46. Okay, this next one, 6 times 10 is 60, plus 6 is 66, times 10 to the power of 2. So that's 66 times 1 with 2 zeros behind it. That's 100. And so this becomes 6,600. Okay? Again, this is the number that I'm looking for, the 6,600. If you wrote it as 6,600, that should be fine. But I have seen this before, 6.6K. No, don't do that. Don't do that. Okay? Now, as with these, I apologize at how late I'm getting this video out, but I mean, I am going to be checking my email and stuff a little bit over the weekend, since this is finals week. So if you have questions, email me and I'll get back to you. It may still take a while, but I'll do my best to get back to you. Okay. So the next part, where you're doing calculations, are looking at resistance in a circuit. Okay. When we've already talked about this some. The electron flow always goes from the negative end of the battery. If you're using a battery, it's going to reach the resistor. It's going to do exactly what a resistor says, which is it's going to help resist some of that electron flow. And So it's going to slow it down, which can reduce the current, but it's going to travel over the resistors. And you can see from this circuit, there's only one way that the electrons can move. There's only one way that the current can go. Doesn't matter the placement of the resistors, it can only go that one direction. And in this case, it has to cross all three. So that is a series. That is a series circuit. That's a series circuit. And so the formula for a series circuit just is the sum. It just means to add it up. If this were a math class, you would see something more like this. You would see it written more in that format. And as you go into math, as you go in your math classes, you'll understand maybe a little bit more about what that means. But so this is, to write it out just a touch more formally, since there's three, it's going to be resistor 1 plus resistor 2 plus resistor 3. But what are they? Well, that's just 4 plus 6 plus 8. And I know I wrote it backwards from the current flow, but it doesn't really matter when it comes to addition. The order doesn't matter. And so 4 plus 6 is 10, and then plus 8, that is 18. So what that means is that this circuit, it has the three resistors, but it is going to act the same. It's going to act the same as if you had a single resistor that had 18 ohms. Okay, and that's really important because that's going to help us resolve things a little bit in the future. All right, so this next one, the one here on the right, this is R1 plus R2 plus R3 plus R4, and this time I am going to run in the anti-clockwise or counterclockwise fashion. There's 4 resistors. So the total resistance is just 3 plus 1 plus 2 plus 4. 3 plus 1, that's going to be 4. 2 plus 4 is 6. And so 10. So that total resistance is going to be 10 ohms, which you just give me the number 10. Give me the number 10. All right. Now this next part, before I get into the parallel circuits, there's something that we do a little bit of work up front. It's going to make your life a little bit easier. And this is the real realm of mathematics. I hear it all the time. Oh, I used to like arithmetic until they started putting letters in it. I used to like math until they started putting letters in it. No, you're not liking math. You're liking arithmetic. Okay, you're liking the basic. That's kind of like saying, well, I like the letters until you start putting them in words. Okay, it's the absolutely fundamental basics. Okay, what math really is using the logical reasoning that you develop from math, from the math class, to apply it into problems. And I'm going to go through this. You're not going to know what I'm doing until we get to the final answer, and until it's when you see the conclusion of what is done with the math that you kind of can start to see, oh, well, okay, that is kind of nifty. That is, and we'll go from there. So I'm starting off with 2 fractions, but before I do, I want to point out this little statement that I have over here on the right in blue. If m equals n, then n equals m. That sounds kind of like a duh statement. So one way to think about it is, if I said that $1 is equal to 4 quarters, then it is also true that 4 quarters equals $1. What that says is that we can just transpose the sides on the equal sign. What was on the left we can put on the right, and what was on the right we can put on the left. But we have to do it in one motion. Okay. Now so let's get started with this fraction. A over B is equal to C over D. I want to get the B out of the denominator. So I'm going to multiply both sides by B. When I do, the B's are going to cancel out on the left-hand side. And what I'm left with is A is equal to C times B over D. I don't know if you remember, but if you have a fraction and you're multiplying it by a value, you can put that's equivalent to putting that secondary value in the numerator. Okay, it can go into the numerator, it can go to the side, but it cannot go in the denominator. All right, so now I've got this new fraction, A equals BC over D. All right, and I just applied this little property here to say C times B. Sorry, no, I got a little bit ahead of myself. I just use property of multiplication that says two numbers, when multiplied together in multiplication, are commutative, meaning that they're the same forwards and backwards. 2 times 3 is the same as 3 times 2. Okay. I want to do the same thing now, but to D. I'm going to multiply both sides by D. That gets it out of the denominator on the right-hand side. And so then what I'm left with is A times D is equal to B times C. And you may be wondering, what does this have to do with anything? And don't worry, I'm getting there. A times D equal to B times C. So now I want to move the A. So I'm going to divide both sides by A. A's will cancel out on the left-hand side, and I get that D is equal to B times C divided by A. So now let's divide both sides by C. C's cancel out on the right-hand side, and I'm left with DC equals B over A. So now I'm going to use this property where I can just switch the left goes to the right goes to the left. So I get B over A is equal to D over C. Now all of this is mathematically correct. I didn't break any mathematical rules. And when I write it directly underneath the original, you'll see that what we did is we took the reciprocal of both sides. The denominator goes to the numerator, and the numerator goes to the denominator. That is going to simplify our work. That's going to simplify our work. And so when I'm going to label this, I'm going to call it Rule 1. All right. So now let's take a look at a parallel circuit. Okay, parallel circuit, it's the 1 over the total resistance is equal to 1 over the first resistor plus 1 over the second resistor plus 1 over the third resistor, and so on. Okay? So parallel circuit. We're going to leave from the negative node, from the negative part of the battery, and then I reach this particular node, and you see there is a choice. The current can either go up to this first resistor with a value of 1, or it can move towards this next node, and then it has a choice again. It can move up to this resistor of 2 ohms, or it can move to the resistor of 3 ohms. Okay, so that's when we're talking a parallel circuit. It essentially means the current has, and I call it a choice, but that doesn't mean that the current can think. It just means that it has the possibility of going one direction or another. And sometimes the way that they're designed, it can be several directions at one time. With this particular layout, it's a binary choice, but that doesn't mean that that's actually how it works. It could manifest itself a little bit differently. Okay, so this is a 3 resistor parallel circuit, so it's going to be 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. I input the values, so this is 1 over RT. The resistor 1 was just 1, resistor 2 was 2, and resistor 3 was 3. All right. So now I look for the least common multiple. The least common multiple of 1, 2, and 3. So when we're talking about the least common multiple, we're talking about the smallest number that is divisible by these 3 values. And that number ends up being 6. So then we create the equivalent fractions. I need the denominator to be 6. What do I multiply 1 by to give me 6? It's going to be 6. I have to multiply the numerator by the same value. So it's 6 over 6 plus. Then I get this 1/2. What do I multiply 2 by to give me 6? It's 3. I have to multiply the numerator by that. So that's 3 over 6. And then I have denominator 3. What do I multiply 3 by to give me 6? That's 2. So then I have to multiply the numerator by 2. And I get 2 over 6. And then combine your numerators. So this is 6 plus 3 plus 2 over 6. 6 plus 3 is 9. And 9 plus 2 is 11. So then this is 11 sixths. 11 sixths. So I get 1 over RT is equal to 11 over 6. Now I go back and I use that rule 1 that says I can just flip both my fractions. And of course RT divided by 1 is just RT. So the total resistance is 6/11. But there's a little bit of there's an easier way to get this number. In a normal math class, I would wait a while to tell you how to do this, but I'm going to show it to you. All right. So go to Desmos. You can go to desmos.com, and then type in your fractions. This was 1 over 1 plus 1 over 2 plus 1 over 3. And you see I get this 1.833333333. But if you look at the left, if you look at on the left side, you see this circle with 2 squares on it. If I just click that, it converts it into a fraction. And then there's that 11 sixths. And so then you know what to do. All you have to do is flip the fraction. And then to get the final number, you just say, well, 6 divided by 11 is, and so then you would put down 0.55 would be it, when you round it to the hundredths place. And so that would be your answer. Oop, my bad. There we go. I did it again. Let's try it again. There we go. Okay. All right. So let's step it up a notch. Let's look at this second one. It looks scary, but it's really not. It's really not. The current is going to flow from the negative lead, and it hits a parallel circuit. So this is let's do red. Okay, 1 over RT is equal to 1 over 8 plus 1 over 6. That comes from that 8 and that 6 respectively. All right. I want to show you just a little trick about finding the least common multiple, and that is, since 8 is equal to 2 times 2 times 2, and 6 is equal to 2 times 3, right? I want to look at these kind of unique set of values. Okay. They both have 2, so I'm going to count that one time. 8 has a 2, but 6 doesn't have a 2. 8 has another 2, but 6 doesn't have that other 2. And 6 has a 3, and the 8 doesn't have that 3. When I multiply all of this together, I get 2 times 2 is 4, 2 times 3 is 6, and 4 times 6 is 24. That's my least common multiple. There's another thing that will happen to it. There's another element that's going to happen to it. Because when I look at 1/8 and I'm trying to find that equivalent fraction, I know I need to get it to 24. And so I say, what do I multiply 8 by to give me 24? Well, that's 3, so then I multiply the numerator by 3. But if you look, so there's my 8. That 2 has been duplicated, and if you look at what's left, it's the 3. Okay? And plus 1 over 6. Now I'm not going to do it. I'm not going to do it for the rest of these. But I just want you to see that when you dive in, when you actually kind of start diving into numbers and looking at the relations, there's kind of some neat things that happen. 6. What do you multiply 6 by to get to 24? You're going to multiply it by 4, so I got to multiply that numerator by 4 as well. But if you look at 6, there's 6. There's that shared 2. And then we multiply it by 4. So just another one of those kind of, I find them neat, kind of curious that things work out that way, and that's not a coincidence. That's actually a pretty important property, but that's something, if you want to hear more about it, I'll be more than happy to tell you about it later. So this is 3 24ths plus 4 24ths, the 3 24ths and 4 24ths. Okay, add those together, you get 3 plus 4 over 24, 7 over 24. And so now you have 1 over RT equals 7 over 24, which means that the total resistance of this smaller circuit is 24 over 7. And just to show you, that these numbers are indeed accurate. All right, it was 1 divided by 8 plus 1/6. Turn it to a fraction. There's your 7 over 24. All right. So what that means is that this parallel circuit acts as if it were a single resistor. Acts as if it were a single resistor of 24 over 7 ohms. And we can repeat this process now. We can repeat the process. So, I'm looking at that resistor now. So the total resistance is 1 over 2 plus 1 over 4. This is 2/4 plus 1/4, which is 3/4. So 1 over RT equals 3 over 4. And that means that the total resistance is 4/3. So this parallel circuit acts as a single 4/3 ohm resistor. And now we only have the one more. One more to go through. I'll use green. I haven't used green yet for this one. Okay, so that resistor, 1 over RT, 1 over 1 plus 1 over 2. So equivalent fractions. And you get that this resistor is 2/3. Just making sure I did my numbers right real quick. Two-thirds ohms. All right. And then what you're left with now, it's not that you actually changed it, but what this is equivalent to is now a series. With resistor 24/7, 4/3, and 2/3. And I'm just you know what, I'll do equivalent fractions, because these are 3 and 7 are what are called they're both prime, and they're also something that's called co-prime, meaning that they do not share any common factors. So that means the common denominator is 7 times 3, 7 times 3. So you're going to get two fractions with 21 in the denominator. 24 times 3, that's going to be 72. And 6 times 7 is 42. Add your numerators. 72 plus 42 over 21. That is 112 over 21. And I don't think that's going to reduce any. So that would be your final answer. I know that was a lot, but this is a video. Go back, watch it again, and see what's happening. Okay. And then we get to this one. Okay, I'm not going to go through and do all of the numbers. I just wanted to set this up, so that way you could see. Yes, this looks intimidating. This looks terrible, and I think, I think we too often, if things look difficult, we don't even try it. But it's really not that bad when you look at it. Follow along and see what happens. The current starts at the negative node, reaches that first resistor. Can't really do anything there. So then it goes to this. It goes to the second one. Like, it has to pass over that first resistor. It gets to this second set, but that's parallel. It's got a choice. It can either go up or down and cross over resistor 2 or resistor 3. The subscripts R2, R3. That's resistor 2, resistor 3, shorthand. So this is a parallel. And the last resistor that I had was 10, so I'm gonna start with 11. There was 10 up here. Okay, but that resistor 11 is going to be 1 over R2 plus 1 over R3, and we've already seen how to solve that. So what's going to eventually happen? You're going to work through, you're going to work through this. And some math magic is going to happen, and you're going to get that R11 equals some number. And so this circuit that is parallel has the same resistance as a single resistor, whatever that value is for R11. And then the current is going to continue forward. And you can see it can either take the first, the second, or the third path. It does have to follow one of those three. It does have to follow one of those three, but it can go either one. Right? The rightmost one, R9, resistor 9, it's easy. That we don't have to do anything with it. The middle one, that's a series. The middle one is just a series. So what I'm going to call R12 is just the sum of those two resistors. And so it will act as a single resistor, because you're going to get, you're going to get some number. You're going to get some number, and I'm just going to call that R12. I don't know what that number is, but that's what's going to happen. The leftmost or innermost is another parallel. It's 1 over whatever the value for the fourth resistor is, plus 1 over the value of the fifth resistor, plus 1 over the value of the sixth resistor. Use Desmos to simplify that fraction, so that way then you can take the reciprocal of both sides and get your new value for R13. And so this parallel circuit is going to act as if it were a single resistor, whatever that value is. But once again, you see, well, now we have another parallel circuit. And I'll call that one R14. I'll call that one R14. But it's parallel. So it's going to be 1 over that resistor is equal to 1 over whatever that value for 13, that 13th resistor was, plus 1 over that value of whatever the 12th resistor was, plus whatever value was given to that 9th resistor. And so you're going to get that R14 is equal, it acts equivalently to this 14th resistor, that sum value. And so all of this will collapse down. All of this will collapse down into an equivalent single resistor. And if you look now, you see that now. And before I finish this, it's not that we actually changed the circuit. What we're saying is that these are equivalent circuits, because you're going to get the same voltage, you're going to get the same current, and you're going to have the same total resistance, because now the final is this series, which is just the sum of these different resistors. And so then that would be your final answer. It starts off complex, but if you go back, listen carefully to how I'm explaining it, and just look at what we're doing, look at how we approach this problem. You see, it's not that terrible, especially since for like these kind of calculations, I'm saying use a program that, no matter how complex the numbers get. Let's just say I had 1 over 14 plus 3 over 8 plus 9 over, let's do 120. That would be that would be really tricky, to do, especially by hand. But I'm telling you that you can just use Desmos and reduce that fraction. Okay, That makes things a lot easier. And so this problem that started off very intimidating looking ends up not being that complex of a problem. And on top of that, I went the problem that is somewhat like this on the test. I went to a pretty high extreme to make sure that the numbers come out fairly simple. So that way it doesn't get too messy. All right, so that's it. Again, I apologize that it took so long to do all of this, but if you have any questions,